So my presentation is based on an article which is just published. And I will show you in a minute the first page of that. And it has been co-authored by Fred Babonneau and Marc Pierre. And this paper was in a special issue of journal, Central European Journal of Operations Research, to celebrate the 100th birthday of colleague George Lightman, who was a professor at Berkeley. And sadly, he passed away just 4 days before his, 5 days before his 100th birthday, which was, I suppose, on the 25th of May. Okay. So this is the journal that I was referring to, and it is the paper that I will use for my presentation. So the journal over there is the journal Central European Journal of Operations Research. I was wondering why they chose this journal for the commemoration, and I understood after all because George Lightman originally was from Austria, and late in his life he came a lot back to Austria. It was there. So I suppose this is one reason for doing this. Okay, so you can take this reference. I will not use any reference in the rest of the presentation. Everything is on this paper this way, and the paper is available, of course, with an open access. And also, I gave a copy to Olivier. Okay, so this is the famous George Lightman. So why is it important to me? It's because actually he has been an important person in my own career. Actually, he was on my thesis journey, and it was at the time called Doctorat d'État in France. And I was, my supervisor was Augustin Blacquière, who had just written a book on differential games with George Lightman. And so when I defended my thesis, George was on the jury, gave his opinion, and after that, I visited him in Berkeley, and after that, we had a lot of contact, and George was a very important person in the domain of optimal controls. He was always organizing networking, and so he was the editor of several book journals, and was always very friendly. Okay, so this is just to say a few words about this nice guy, who was just rich. Okay, so in summary, what I will present. I refer to what we call an infinite horizon optimal control problem that can model the global energy transition to zero net emission when we have access to CDR technologies. CDR technologies is CO2 direct reduction. And also we had that in this publication, electric fuels, so it could be an important technology in the future. And now if these technologies become available, so, on the practical side, I believe that these technologies are important. These are the technologies that we even if we continue to exploit fossil fuels, as is currently the case, we don't reduce a lot. So we will see that. So the key word is infinite horizon. Okay, as you see, as you saw before, I did my thesis on that. And actually, there was a lot of work at the time on what they call the Hamiltonian system and the asymptotic stability of Hamiltonian systems. It was in the context of calculus of variation, and they were characterizing the solution of optimal control problems by a dynamic system called the Hamiltonian system involving the state variable, state variable, etc. And it appeared that if the system is convex, the optimal trajectories for this system on an infinite time horizon tend to converge, to group together close to a steady state, which is an optimal or an extremal steady state. And this is an attractor. So all trajectories, whatever the initial state, then converge to that. And that was an idea that first was observed by von Neumann when he did his first study on dynamic multi-sector economic model. And he had what's called a balanced growth path, and he called that a turnpike, or so maybe not even, maybe it was somewhere, I don't know, but turnpike, because at the time it was just after the Second World War, they had created one big highway in New Jersey, and this highway was called the Turnpike. The American got this very strange British name, Turnpike, in the place where we put the money in the Middle Age to enter in the town. And so in the States, they use that for the toll, the toll highway. But the idea that the Turnpike actually is a big road, and all small roads converge to this turnpike. And then when you want to go from a place to another one, you go first to the turnpike, keep the turnpike as long as possible, and then leave the turnpike. That was the idea. And then for the infinite horizon problem, you have similar thing, where but now the turnpike is the attractor. So you go there and you stay there. Okay. And I believe that actually this concept of turnpike gives us a good analog to what we call the sustainable future. When you say that you want to convert to a system where you will be in sustainable development, and there is no need to further abatement, no need to further growth, etc. So, and this is a good I would say representation of that, I suppose. And the idea also is that this turnpike, which is the attractor of these dynamic trajectories, can be easily computed. And I will come back to that. On top of that, in our approach, we say that actually on this turnpike, which is now a problem to solve, which is much simpler than the dynamic one, characterize the turnpike. It's a customer transition turnpike. We can implement robustness. So it means that if we have uncertain parameters, we could robustify actually the computation of this space. So making actually they will also more precise definition of this for this application. So this is the mathematical structure of this problem of optimal control with the infinite horizon. So basically, we have this representation, which is really the fundamental representation of an optimal control problem. Infinite horizon, because you look at the integral from 0 to infinity of a payoff, where it is a utility function, a joint utility function. And this joint utility function is actually, here it is a joint utility function, which is the weighted sum of the utilities of each coalition of countries. We will consider just 3 coalitions of countries. And here you have a utility which depends on the state variables. And this is the state equations. So the control variables and some extra variables, so that some variables are just exogenous variables that you fix. You have no control on that. Or it could be what we call passive variables, also auxiliary variables and passive variables. So auxiliary variables which serve in the computations of constraint, and passive variables which are not affected by the control. And so the system here has a general state equation. It has constraints involving the control and the state, and an initial state. It starts from the initial state. Okay. So this is the basic infinite horizon, generic infinite horizon control problem. Now, if when t tends to infinity, you have a stabilization of the different functions. So it means that you have now, as you notice here, all the functions, utility, state equations, etc., depend explicitly on time. But now, if when t tends to infinity, if t disappears in this function, they become what we call time independent or stationary function. And you see you have, so I call this function L bar, Fj bar, Jj bar. And the idea is that if you have a system, an economic system, which is set for controlling sufficiently convex, so you should have convexity. Then, when you go to infinity, there will be an attractor, which will be called the turnpike, and which is actually the in a sense, a steady state optimal trajectory. But it is optimal with discounting. So if the discounting is 0, if the discounting, if rho is equal to 0, if we're there, so here you see you have just the utility, and here you have just the state equations where you replace the derivative with 0. So you say now the system is stationary. You don't change the values of the capital stock, but you do that of the state variables. And you satisfy the constraint. So you have now an optimization plan, which is a simple mathematical programming problem. You don't have differential equations, etc. It's much simpler to solve. And but if rho is positive, the turnpike is not exactly an optimization problem, because it is actually a steady state equilibrium trajectory. So it means that you should compute that by solving actually the Hamiltonian system and imposing steady state. And it has been shown that actually you can define what we call an implicit optimization problem, where actually you have here the utility, stationary utility. You have the stationary constant as before, but instead of having just 0 equal derivative of the state variable, you add this term minus rho is a discount rate, xi, which is the state variable for the player I, minus x bar I, that should be j is x, well, xj, xj minus x bar j. So, and the x bar j, which is here, should be the solution. So, the idea that you should have a solution of this optimization problem with a constraint like that, but the x bar, which is here, should be equal to the solution. So it means that it is actually a fixed point. It is a fixed point problem. You fix, for example, this x bar j, which are the turnpike values. You imagine what they are. You solve this problem. You have now a solution which gives some values to the xj. They are different from the one we used before. So what you do, you change the one we used before, you put a new one, then you would do it again. So this is called the cobweb approach.
Now, what will change if you start with functions that are not explicitly depending on time? If you have an autonomous problem, you cannot do the same thing?
Yes, the same thing. No. It's just that actually in all these economic models that we consider, there is explicitly dependence on time because you have technical progress, etc. So it's fine. But actually, it could be extended to many cases, and also could be extended even to non-autonomous system where you have not a steady state at the end, but this balanced growth. That's why the opportunity. But here we look for the steady state solution when things stabilize. Okay. Do you follow me on this? So it means that in order to find this attractor, we will have to implement a fixed point search. So we formulate this problem with an a priori idea of what are the turnpike value. And then, for example, you start with a solution with rho equals 0, for example, so it's simple. And then from that, you enter the value 10 there, you do it, and then you update. And it converges rapidly.
How do you solve the infinitizing problem if rho is equal to 0?
Okay, if rho is equal to 0, the solution that we consider is the famous overtaking optimality, which is actually, okay, if I answer it, because of this turnpike property. Actually, if you have rho equals 0, you have all these. If you have rho equals 0, all these integrals tend to infinity. So you say I can't do it, but in fact, there is a technique which is called reduction to finite constant finite utility. It means that instead of taking the utility over there, you will take actually the utility minus the turnpike value. So the difference between the utility you have and the steady state. And this is, and when you integrate this over an infinite algorithm, it is finite. Do you know a little bit Markov decision processes? You know that? MDPs? yeah, the Markov decision processes, we could have MDPs with discounting, and we have MDP without discounting. And in the dynamic programming solution, without discounting, you remember you have some values. They are not the value functions, but they are some values, but they are exactly this reduction to finite cost. Is how much it costs in addition to be far away from the steady state. This is okay. This is yeah. It's interesting to discuss that. So it's the okay. So in our application, we define an economic and energy technology sector model, donc a model which has several sectors in economy and in technology. And then we have actually a general economic good that can be consumed, invested, as the basic optimal growth model. And then you have different level of energy form. So you have fossil energy, renewable energy. You have technologies, dark CCS, which is a technology that captures directly CO2 in the atmosphere. We have BCCS, which is a technology that produces electricity from biomass and captures the CO2. We have ERW, which is enhanced rock weathering, which is a technology that produces negative emissions by disseminating some minerals in the nature. We have then e-fuel, electric fuel, which is an interesting technology that I should describe a bit further. And here I have a representation of the structure of this economic world. You have here the production of the general economic good, which uses capital, labor, and energy. And this energy is the useful energy. Then you have here the technologies that capture CO2. And then we have three technologies that capture CO2. We have as I said before, and each technology uses some capital, labor, and energy to do the capture. And then you have the BCCS, which uses capital, labor, and biomass. These are the different technologies. Here you have the energy levels. Here you have the level of useful energy. Here you have the level of secondary energy, which can be fossil, renewable, or coming from electric fuel. In the fossil energy, you can have oil, gas, or coal. And each of these primary energy sources generate emissions. So the emissions are just proportional to the use of these different energy forms. So this is quite standard, except that this structure is really based on a view of the whole system as a hierarchy of production functions. And each of these production functions we will represent by the so-called CES function, constant elasticity of execution function, which has the interesting property that a production function like that can be calibrated or identified with the observation of one equilibrium. So you start with the current equilibrium. And with that, The only thing that you have to imagine is the elasticity. Elasticity, which is difficult, that has to be estimated with difficult system. So usually one gives value of that. And for the rest, it's immediate. So I put in the archive that I gave to I put the GAMS program for what I present here. And this GAMS program has the first part, which is the identification of all the CS functions. So we do that directly in the program. The only thing we give is the current values, monetary terms of the current product. The approach we get for representing climate policy is the approach based on the Safety Cumulative Emissions Budget, SCEB. We say that actually, with all this research on climate change, temperature, etc., we came to the observation of people very early. But what was very important was the cumulative emissions. Already, my friend Richard Leroux, long time ago, said, we just have to add a constraint on the cumulative emissions. And it seems that now you can say that, for example, reaching the target of 2 degrees C temperature increase with more than 60% probability, requires to have to limit the emissions of the cumulative emissions since the beginning of the industrial revolution to 1 trillion tons carbon. So actually, we can deduce on that all and we come to the evaluation that it remains 1,070 gigaton CO2 to emit cumulative. So this is the budget, and we should not go over that if we want to be able to reach the goal. So this is very, very practical because you don't have then to enter into the computation of damage and let's see. It will be then it will permit you to use what we call not the cost, it is the cost effectiveness analysis, but you just put the constraint on the cumulative emissions. Then we have also put, in order to show the implementation of the climate policy, simplest way is to imagine that there is an international emissions market. As I said before, we have different CDR technologies and 3 capture and 1 e-fuel production. And the e-fuel is interesting, and I believe that there should be more emphasis on that, in particular for countries like, or regions like Quebec that has a lot of renewable energy. The e-fuel comes from solar energy that is used to extract hydrogen from water and also used to take CO2 from the atmosphere, like that. And then the CO2 is used with the hydrogen to produce a fuel. And this fuel is zero net emission because the carbon comes from the atmosphere. So it means that you produce something that doesn't fit. That's interesting. So now the model has a lot of control variables. There is no reason to spend time on that. the passive variables, as I said, that are used to compute things, they are the consumption, the economic good production, the damages that are computed from the temperature change. But you can put that in the model, even if it doesn't serve a lot of purposes. Then the price, action level, a lot of parameters. And these parameters are mainly the coefficients that appear in the production function, the CS. So as I said, what is very important, the evaluation we have of the elasticity of substitution. Then we have to enter the price of the primary energy and some coefficients that describe the technical progress in different sections. So the acronyms, just to repeat: electric fuel, enhanced rock weathering, CDR, carbon dioxide removal. Voilà. But yeah, I said CO2 direct removal, it's carbon dioxide. So now the formulation of the control problem, the generic one I gave before, now it is the one that I am interested in. So it's again the weighted sum of the utilities. The utilities integral over the infinite horizon with discount rate. This is the population level logarithm of per capita consumption. Consumption divided by population. So this is a standard type of utility function. The consumption itself, which is here, is the production reduced by the damage, minus all the investment you do in the different sectors, capital sectors, minus the price of energy. And if you wish to be fully correct, you have then here to add the revenue you get on the market of permits. And with omega will be the quantity of permit you put on the market, and EM is the emissions you do. PM will be the price of permits. So if you put on the market more than you need, you get money. If you put on the market less, you owe money. State equations, it's a standard state equations for capital accumulation. And then emissions budget. So as I said, the budget is the safety cumulative emissions budget. So the variation over time of the remaining budget for emission or clear is decreasing with the quantity of permits this coalition puts on the market. But it is replenished by the negative emissions. So it means that if you have negative emissions, you can rebuild those stuff. Okay, this is the interesting thing of negative emissions. Then there is an initial value for this budget, which is the share of the total 1,070 gigaton CO2 that is given to each coalition. So I took 3 coalitions. And so we have then a distribution. Theta J is what is the share of this total budget which goes to each coalition. The 3 coalitions are the BRIC, the OECD, BRIC, and the rest of the world. And typically, we will give a lot to brick, another load to the rest of the world, a little bit to Greece. Okay. In order to be fair. So all these questions of fairness in the use of the emissions budget is another story that I will maybe have time to discuss. Okay, now we can impose that the summation of the budget, which coalition, remain non-negative. And so this is something that will prevent what we call overshooting. In many models, you let the temperature go up and go up above and then here it will not work. Yeah, here the idea is that you are not allowed to do that because you will not be permitted to emit more than what guarantees. Okay. So this is the idea, and you can even prohibit overshooting for each coalition. That it will be too much. So we use this approach because myself, I am not convinced at all that if we let the system go over the limit, you will just at the end your it's very difficult to say we will emit a lot and then we will capture a lot.
Barbecue everyone.
Yeah, this is the effect. Okay, that's the idea. Okay, and then we put all the production functions are CES. So it means that this is a structure. So we have always written the constraints with inequalities because it facilitates the solution. We have all these free disposal assumption. So as you see here, you have this is what we call the total factor productivity, and then you have a share of the production factor in the production function, and here is exponent, which is composed of the elasticity. So that is the usual function that we have for production function in economics, and we have extended that for representation of what is produced by the negative emissions technology. For BECCS, it's a little bit difficult because in most models, BECCS will be considered as an electricity production technology. And here we consider it as a negative emissions technology. So in most of the models, bottom-up models, we will have BECCS, which is an electricity production technology, which as a byproduct has negative emissions. In our case, it's the opposite. We say this is a negative emission production technology, which as a byproduct produces directly the useful energy. And what is clear is that the content of energy produced is just proportional in the quantity of biomass used. It's the energy coefficient of the biomass. So it could be represented this way. This is because first we did the other way around, and it was very difficult in this structure of modeling to represent BECCS without double counting, etc. The labor has to be used in the different sectors. And then we have bounds on sequestration. How much negative emission you can put actually in in storage, permanent storage. So we say that for each region, there is a limit on how much you can capture from different technologies. And what we have here introduced in the model is some robustification. It means that actually, instead of using directly the bound that we obtain from the observation of what is described in literature, etc., we will put actually a robustified constraint. And this robustified constraint, so we say that actually the quantity which is possibly sequestered is not bounded by that, but by a value which is defined here. And actually, this is not each quantity, it is just the sum of all the constraints, the sum of all captures. So we put a constraint on the sum of all captures. And we will see how we define this constraint. In this formulation of control, you can easily put equations for imposing penetration bounds for new technologies. So this is called as the S-curve or logistical function, etc. Okay, I will not insist on that. Useful energy generation. So you have different, the energy used in the general economy plus the energy used in the two capture technologies minus the useful energy coming from the CCS will be composed of fossil fuel, renewable, and electrical fuel. Fossil fuel, as I said before, you have the fossil fuel will be produced from refineries, etc. And here you have the fossil energy source used, so it's a primary, used to produce the secondary energy. And this primary one will be composed of coal, oil, or gas. And the refuel, this is the thing which is interesting. We model it from a technology which has been recently publicized, which is a company which is called Terraformer and Terraform. So it is a compact plant, a small plant, which integrates directly the 1 megawatt solar energy system. There is no electricity transmission cost. Contains an electrolyzer that makes hydrogen from water, and a Sabatier reactor that combines the two, so hydrogen and CO2, to make the synthetic methane. So the whole thing is powered by solar energy, so no emissions, and almost no cost. In our approach, it is modeled as just being produced by capital. It's something which costs a lot because you have to have it. And what is interesting is that you can find that in an issue of The Economist, a good British journal, in November 2024. It was some advertisement And the guy, Hammer, is the one who manages this Terraform. And he says that solar power is changing the economics of energy. So he says that actually, currently, he pretends that he can produce natural gas, which would be competitive with the natural gas more consumed in Europe, not the one in North America, but for the natural gas that comes to Europe after it is liquefied, transported, etc. It says that the fuel is competitive. That's interesting. Okay. And then the renewable secondary energy is also produced by capital, essentially. And all the TG emissions come from, as I said, the primary energy sources. And the market. So we can model easily this international emissions rights market by saying that actually the different players or coalitions of countries have to put on the market more than what they emit globally. And there will be a price that should be equal to the marginal abatement cost. And it will be the same for all coalitions. So you equalize, so it is efficiency, you equalize the marginal abatement cost, and this gives you the price. So now we compute the famous turnpike. I will not, okay, so we have this implicit optimization problem, which means that actually the only thing that you do, this is now the capital accumulation constraint or equation. But here we say that the investment is equal to the depreciation. And so if RSS now is the steady state discount rate, and so if RSS is 0, so you have the standard thing where in steady state, you replace the capital as it was at. If RSS is positive, then you have to include here this extra term, RSS, the steady state capital stock minus the turnpike value. And just at the solution that we have, you want to have turnpike and cable. So to understand that, the details of why, etc., you may go back to a book, famous book, which is by Carlson, Haurie, and Lazarovich. So this is also one of the three authors dead since time, but I am pleased to see that Carlson is still alive, and myself almost. Okay. Infinite horizon optimal control, and then in that you can see all the details of what I referred to. What is interesting is, thanks to Lazarovich, we can make here in this book the links between the deterministic and the stochastic systems, and as I said before, find the correspondence with dynamic programming in stochastic systems. Okay, in this steady state, the environmental constraint is just to have zero net emission. We don't want to emit anymore, because if we emit, temperature will go up. So we have now spent all the budget, and we should not emit anymore. So net emission should be zero. in sustainable steady state. So here the term E3, which is here, is because as in DICE, we have introduced extra emissions coming from which is not the emissions linked to the energy. Okay. As I said, we wanted to put some robustification because, in particular, the capacity of stopping negative emissions is maybe uncertain. So the idea that we will try to robustify not every constraint for the different correlations, but one additional constraint that we have, which is the sum of all negative emissions a priori should be lower than the sum of all capacity existing. But this is something that is uncertain. Actually, what is uncertain is the capacity for each correlation. But we are at this one, we're saying, okay, actually what is interesting for us is the sum of what is the total, because this is what is important for the environment. So here I have all the development of the robustification, and maybe so it pays, okay. It's interesting to go in the detail because this is what is a little bit original in this approach. Fact is that for each correlation, you have the capacity of stocking, which will be actually the real capacity, which is a nominal capacity, the one you have from the literature, for example, and something which will be a random variable, which is a priori a random variable with support -1 watt, and here an error term. Meaning that you could have things that vary. Could be more or less for each one. And so you can rewrite the global constraint before sum of all the sequestration or the capture will be below the sum of all the nominal plus some error, and the sum of all the error. And then what we do is that we define what we call an uncertainty set for the all the errors. So there will be a vector of the random variables -1, but this is a vector of three-dimensional because that's three Polish. And we define here just what the sphere. We say that we look at all the values for psi which satisfy this constraint, which is like if we have two dimensions, this is a circle. You have three dimensions in the sphere. And if it is m dimensions, this hypersphere. And this radius is called it defines the level of uncertainty. The larger this uncertainty set, the larger the uncertainty that you take into consideration. And then you take the worst case for this constraint in this uncertainty set. But this is the trick. The fact is that if we would take, for example, the worst case for each country, so -1, -1, -1 for everybody, it will be too much. If you take 1, 1, 1, 1, 1, it will be too optimistic. So you have to find in this sphere the worst case. And you take this worst case, and it can be shown that actually it ends up as, sorry, this is the technique, it can be shown that it ends up with this constraint. The sum of the capture must be smaller than the sum of the nominal values minus the square of the sum of the square of the errors. And so you can add that to your model, and you see that actually you will not capture exactly the sum of the potentials, a little bit less, but it will not be the minimum. And after that, we can use this constraint everywhere in the transition. So this constraint which applies at the end, we could use it in the transition. In the theory, we can, using some kind of Chebyshev inequality, something like that, attach probability of that. So here it is the dimension of variance. The square is root is the dimension of standard deviation. If you take k equal 2, for example, you get the around 95%. The probability of satisfying the constraint. Okay, so now we run the model. Definitely, I make a presentation which is more oriented towards the mathematics than the economics. And we get that. So we get what we call a sustainable bliss point. So if you, did you read the famous paper by optimal accumulation path? The most cited paper in economics, the Ramsey paper, which is 1928, where he uses calculus of variation to represent the optimal accumulation of capital in the economy. And he says that actually we should have an asymptotic value, and he said we should not have discounting in general because of ways, but he said, I just can't compute things with the discounting because at the time he was not aware that he could do the trick of. But he said that in the case of zero discount rate, he called the solution attractor, which is the turnpike. He called that the bliss point. Bliss point meaning that everybody is happy. And this is it. We have the bliss point. So in our case, we find the asymptotic steady state. And here I show what is the situation at the bliss point, and here what was your initial situation. What is very important, the thing that is very important is to look at the per capita consumption. This is something that, if you say this is in $1,000, so it means that in this bliss point, because we have technological progress everywhere, and in particular for European countries, etc., you have $45,000 per capita in OECD. You have $25,000 for BRIC, and you have 17,000 for the rest of the world. And you compare that to the current situation, where you have 23,000 for OECD, 350 for BRIC, and 205 for the rest of the world. So in this case, you see the enormous progress in the Greek and rest of the world. A factor of 8 in this trend. Now the second thing is the emission level. It is 1768 gigaton, and currently it was 20. I think 2020 it was 28. So it's not even half. So you continue to emit a lot. So Petro-Canada is happy, and the situation. And of course, this is due to the fact that the population itself. This is also a very important thing to look at. The population. If you look at the total population at the steady state, is 10 billion people, or almost 11. And currently it is 700 million. So it is, it is 7 billion. So it means that actually you have a growth of population, and the growth of population is mostly the rest of the world, which is 3 to 50, and it doubles. And this is okay. So there is a big price population in the rest of the world, and actually almost constant population in OECD. So which is the situation, and it is a good summary. You have to make developments considering that actually there will be a big need of energy in the countries, rest of the world for the BRIC. Then we have assumed that there is a loss of population. This is particularly in China. Actually, in India, at some time. Okay, so this is it. And okay, I gave the thing the CO2 price is interesting. It rises from the current value of $46 per ton to a value of $415 per ton. And so, of course, that would be a high price of everything. Now, for the transition, in the program that I gave, the GAMS program, you have the recent which is going to look at the turnpike and the transition, etc. The transition is actually a program with we solve the optimal control problem by using just a discrete time version of it, which is cheating a little bit, but for optimal control, but we use actually a discrete time version of the model, the triple distance square. And we get that. So we see what happens in the future. So we show her what happens until 2044. It doesn't mean that in 2145 we've reached already the turnpike. The turnpike is even farther now. But nevertheless, you see what happens. The emissions, total emissions, go down, go up, down, and stabilize. So you see here, this is OECD, they decrease, right? This is BRIC, this is rest of the world. So for development, they need a lot of fossil energy. And after that, they stabilize. And here you have the negative emissions which go steadily. Here you have the evolution of net emissions. So you reach in this model, you reach zero net emission before 2100. Usually this is 2018, I suppose, but this even as the limit for the whole planet, and for the OECD country, they want to say 2050 hopefully, but it's not a special. And the temperature change, which is computed with the DICE 2013 climate model. So you see that effectively, with this constraint budget, the temperature is limited at which.
So I'm just wondering how sensitive is like the 2100 to the climate change. So if say some climate change, so this may be like 80.
You say this one here?
Yes.
Sensitive. What do you mean exactly by
So the parameter.
No, this is not the parameter. This is the result of the model.
If you run the sensitivity analysis,
Yeah.
what parameters would affect a lot of the results?
Okay.
Yes.
Okay. I would say that the first one is the budget.
Oh yeah.
Yeah. The first one is the budget.
You mentioned
the second one will be the capacity of storage, because this is the penetration of these negative emissions. But this is rich because of the negative emissions. If you see here, the negative emission, they rise very steeply, and then they get this 17 gigaton value, which is huge. It is huge. Okay. Here is the GDP consumption, and here is the evolution of per capita consumption. So as you see, there is here the growth of per capita consumption, and we impose actually as terminal values for the capital stock, etc., the turnpikes. So in 2180, so we impose a terminal constraint there. But it is an approximation. It should be imposed later on. So it's why on the price, we have heard the price which goes up, but which goes over 600. And as you noticed before, at the turnpike, it is 400. So it means that actually there will be, because starting here, there will be a lot of negative emissions, then the price will go down. Okay. These are the evolution of capital stocks. And I will not, okay, I made all the comments on that. To have more details on the economics of this approach, we have a second paper, which is the same model but described without issues, but with more details on the economic structure and more simulations. And here we see we make some sensitivity analysis, and we compare also the results we get with some other structure. It just appeared, as you see, it has been published, I think, two weeks ago or 1 week ago. This is in the journal of. Okay, that's it.